Hi there and welcome to your next lesson. We're going to be looking at chapter 18.3 today, and we're looking at how to determine the order of a reaction using some graphical methods, mostly the initial rate method. And this is slightly different from what you've done before, but knowing the order of a reaction with respect to lots and lots of different components is really important, because if I'm making a reaction mixture and I'm making a compound for a business, I want to make sure that my reaction conditions are set so that we get the speed of reaction that we require to get the product as quickly as possible. So it is really, really important, and understanding the order will also help us understand how the chemistry works, how the mechanism of making these components actually happens. So let's go to the PowerPoint and we can start talking about it. Okay, so I'll just check that we're still recording because it glitched a moment. Yep, we are still recording, that's good. Okay, so firstly what I'd like to do is to draw or sketch a concentration time graph for 0, first and second order reactions, and also have a think about how the half-life varies, and depending on whether it's 0 order, first order and second order, and maybe have a look at the equation that you could use to work out the half-life. Okay, so let's go actually forward to this. So this is what your graphs look like. Your 0 order is a linear line, and we're thinking this is a reactant, which is why it's pointing downwards, so it is linear. We can see it's not got any bends on it or anything, so it looks very, very unique, very easy to sort of work this one out. Concentration-wise and time-wise for the first order, we can see it looks a bit like a sort of quite shallow curve. This is your normal sort of decay curve, and it'd be very easy to work out what the half-life of this decay curve was, and the half-life should be constant. If we have a look at the second order graph, we can see this is much more steep than a first order graph. And I would say the big challenge is making sure you know the difference between these two curves. We can see that the second order curve does have a much steeper elbow to it, starts off very steep and it shallows out very, very quickly, whereas this one is your normal exponential decay curve. So 0 order, first order and second order. Now, mathematically, especially between the first order and the second order, actually it's quite difficult to mathematically see which one's which. Those of you who do A-level maths and sort of your more advanced maths, how can we do that? If I say that actually the gradient of this one, the 0 order, does not change, so what would the gradient look like if we plotted it, so on rate against concentration, we would see that it would be a long straight line. If I plotted the gradient on this one, so I differentiated the line, we would see that this would then turn into a straight line, and if we differentiated this one, we would see this would turn into an exponential decay curve. So actually by differentiating these, we can work out what the order is very easily, and that's what we're going to sort of work out today. So I'm just going to go back to our learning objectives. So what you're going to be doing is working out what the order of a 0, 1 or 2 order reaction is, and I've got to say, you do not need to know third order, you don't need to know fourth order, you only need to know 0, first and second order. We're going to be talking about rate concentration graphs. So far we've been looking at concentration time graphs, so we're looking at rate concentration graphs, so we're determining the rate of reaction. In order to do that, we are going to be looking at initial rates methods, and that's slightly different to what we've been doing before. We've been monitoring the concentration of a reactant as the reaction proceeds. What we're going to be doing now is doing initial rates methods, multiple experiments and using those to work out what the rate and concentration is. To do that, we'll be doing clock reactions, and this is where we look backwards to Christmas, where we did that sort of silly experiment where we were trying to find out the ideal reaction mixture to go along with the song. I'm sure there's a video that you guys can watch if you don't remember it. It's that reaction we're looking at in slightly more detail. So, we've been looking at concentration time graphs, but actually they're not as useful for determining the order of a particular reactant as rate concentration graphs. And the reason for that is because if you go between the first order and the second order, that curve looks they look very similar to each other. If you were to come up with one of those in exam, you'd have to make sure that it looks very, very first order or very, very second order. But if we look at rate concentration graphs, because they are essentially the gradients of those graphs, it will actually be a lot more obvious what the order of the reaction is with respect to that particular reactant. So you can plot concentration time graphs using your continuous methods, but actually if we're doing a rate concentration graph, it's usually easier to do it with an initial rate method. We have given you the booklet now, so as we go through the next few slides, what I would do is I would go through and fill in the booklet or rewind, etc., as you wish. So, what does a zero order graph look like? And remember, this is rate concentration graphs, not concentration time graphs. So we can see that this is your zero order graph. It has a straight line which has a fixed y component. So we are saying we just have y equals 2 or 3 or something like that, which is going to relate to the rate of reaction. So we're looking at the initial rate of reactions, we're changing the concentration, and we're seeing that actually it doesn't change the rate at all. So this is our zero order rate concentration graph. And we can see the reason for that is because if we look at the rate and we look at the concentration being the concentration of something to the power of 0, that is always going to be a fixed value. Anything to the power of 0 is 1. So we would find that we just have a long line going along there. So we can see the zero order very, very easily. Interestingly, the intercept on the y-axis is going to equal the rate constant. It's worth remembering that because occasionally they will just give you a graph like this and they'll say, right, what's the rate constant of this? And you just have to go to the intercept where concentration equals 0. The intercept is going to tell you this, or in fact, as it's totally linear, whatever the y value is, that is going to give you the rate constant k. So what about first order? With a first order reaction, we know that that reactant is getting involved in the rate determining step, that slow step in the middle of the reaction. And we know that actually if it weren't there, there would be no rate, it wouldn't be happening. So it's important it's there, so therefore it is going to go through the origin. And as we move up in concentration, we know that actually the rate changes in a first order way. It is linear. It's a long straight line. So we now know rate concentration graphs are going to be a long straight line going through the origin of 0. Remember, this is not like the zero order, because the zero order graph was a straight line. The origin, it did not go through the origin. So, as you think about it, if we look at the concentration, it's first order, and that means it is directly proportional to the rate, which is why we have a first order line. It's a linear line. And if we look at the gradient of this line, so we look at the y over x, so rate divided by concentration taken there, that will then give us the rate constant k. So really, really important. This is really nice because it can sort of tell us quite directly, quite easily, the rate constant k, which is why we do these sorts of experiments. Let's look at a second order graph, and we can see that this is a bit like a half of a parabola, because if we do it in that direction, it's going like this. So this is in fact half a parabola. Again, we can see if the concentration is 0, the rate's going to be 0 because this component has to be there for the reaction to happen. Working out what K is going to be somewhat more difficult with this. If you differentiate it again, you'll get a straight line, and the gradient of that would be equal to K. But I do believe that that is beyond what the specification asks us to do. But that is what it is. We have K, a rate equals K times the concentration of A to the power of 2. So it is a square function like that. Now we can see if we compare our first order, zero order, and our second order, they are very, very different. So they're much easier to look at. A quick tip for you, because we're looking at reactants, you'll notice that actually these ones, apart from zero order, are going from the origin and upwards, whereas our concentration time graphs were going downwards. So really easy way to work out which type of graph you're looking at. So this is what they all look like together. And as I said, the features are zero order does not go through the origin. It is a straight horizontal line. First order goes through the origin and is a linear line, and the second order is going to look like a half of a parabola. If you have third order, it's going to look like a cubed function for those of you that do maths. Fourth order, blah, 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 going higher and higher and higher. So what are these initial rates methods? I said to you, I think it was in 18.1, that actually it's easy, or it's most sensible, to take the rate of reaction right at the beginning of the chemical reaction. And the reason for that is because if you think about it, you will then know the concentrations of all of the components to a high degree. And the reason for that is because as the reaction proceeds, we are losing reactants and making products. So actually the most accurate time to take a rate of reaction is at the beginning of the reaction, the initial period of reaction. Now the way we do that is by taking our volume or concentration and time, and we draw a tangent right at the beginning. So we can see this is a sort of curved function, and what we do is we take a tangent of that line, and from that we can work out what the rate of reaction is. Now, there are a couple of reactions which are sort of special circumstances. And the first I'm going to talk about is the clock reaction. And if you want to sort of see a clock reaction, either have a look at the Christmas video that we did. In fact, you guys did that video, so actually you've already done a clock reaction. And there are also other things. So, for example, appearance of precipitate. When you did your GCSEs, you would have done the disappearing cross experiment where you get some sodium thiosulfate, you add some hydrochloric acid, you have a cross under there and it sort of disappears. And there are also sort of colour change reactions, etc. as well. If you think about it, the initial rate is going to be proportional to 1 over the amount of time that you've done it before. So initial rate is proportional to 1 over time. That is what that sort of alpha type thing means. It should have little sort of tails on it as well, but PowerPoint is a little bit restrictive in what we can do about that. If you do want to see some quite cool initial rate clock reactions happening, have a quick look at this YouTube link. I will add it to the end of the video. So this is the disappearing cross experiment that I mentioned earlier. And if we look, what happens is this is the start. It has like a nice cross on there. It then makes a load of sulfur, makes a load of sulfur dioxide, which smells horrendous, and the cross disappears over time. We always do it, or I always used to teach it in the way that it's a bit subjective, because different people will decide that the cross has disappeared at different times. So I use it as a way to sort of train people in the scientific method and go, okay, this person thinks it's gone this time, this person it's gone this time. So putting control measures in to make sure that you understand, the same person has to be watching it. You have to use the same cross, etc. But this is something where actually you can measure the initial rate relatively easily just by looking at when the cross disappears, and then knowing a little bit about the chemistry, knowing what that is. It's usually something that you're given an equation to tell you what the initial rate is given the time it takes for the cross to disappear. So if we did that experiment, we would find that actually if I increase the concentration of the sodium thiosulfate, it will have a linear line when we're looking at the rate versus the concentration. And because we know it's a linear line, what order is it with respect to the sodium thiosulfate? If you thought first order, you're absolutely right. We can also see very, very easily that the concentration of HCl has no effect on the rate. It has to be there. We have to have some HCl for the reaction to happen. But what happens is the rate determining step, the slow step, does not involve the hydrochloric acid, so therefore its concentration does not change the rate. So we can see that the order of reaction with respect to the sodium thiosulfate is first order, and the order of reaction with respect to hydrochloric acid is zero order. So this would be what the rate equation would be. It would be rate equals K times sodium thiosulfate concentration. And how would we work out K if we had that equation? Yeah, we would literally just take the gradient of that line, and that would give us K. And in fact, we can get Excel or something like that to actually do that for us. So we just put the data into a spreadsheet, and it will tell us directly what the rate constant is. So we've said about iodine clock procedure. This is a really, really nice experiment, and this is the experiment that you did at Christmas. What we have is we have several components. Two of them are competing with each other and trying to make iodine, and the iodine is then being, I think it's being reduced. Anyway, it's being either oxidized or reduced and turned into the iodide. Wait, so oil rig oxidation is lost. Yeah, reduction is gain. So it's gaining an electron and becoming iodide. And then when the initial component runs out, that's when you start seeing the color. But have a look in Caboodle at the textbook. It says 20 to 22 in your textbook, which is our second year textbook. In Caboodle, it may be on a slightly different page. Have a look and see what they talk about when they're talking about the iodine clock procedure. Make some notes about it. This is an experiment that actually it's worth knowing about. You don't need to know the full components of it, but just how we would end up working out what the initial rates are. Just in case you do have trouble finding it, I'm going to put the text of that on the screen now. Please feel free to pause and have a look at what it says. There are some questions as well, which I'll be flicking to in 5, 4, 3, 2, 1. Have a look at those questions as well. You have done some work on a spreadsheet which will really help you. This will sort of supplement them, but if you have any questions, we've got an worked example for the clock reaction, and it will help you understand the science that we're talking about. So, how accurate are they? We do have a bit of a problem because our colour change, or whatever we're looking for, will happen after a certain time. So we can see here, when we've got the colour change happening very, very quickly, actually this is a relatively good measure of the initial rate, because the initial rate is going to have a very similar gradient to the initial rate next to it. So what we normally find is, if we're doing one of these types of reactions, we are given a correction value. It will tell you what you need to times it by to ensure that you have the initial rate, and that will have been sort of worked out in the past by lots and lots of experiments. But it's well worth knowing that, and it's worth knowing it's not the be all and end all. To get the initial rate, you need to be going straight away at the rate of reaction, and it is actually quite challenging to do that. There are a few experiments where you can do that, but actually it does represent a little bit of a challenge. But we can see here that actually, if the colour change was here, if we just had that as the rate and the initial rate, it would not be very accurate. Right, so here are some tasks for you. Have a quick look through the textbook. As I said, you are going to have to go to Caboodle for the electronic version. We are going to try and get these textbooks as soon as we can get them, but obviously they need to sit for 72 hours before we can do anything with them, because someone else has touched them and things like that. But we will try and get you them as soon as possible, but you do have access to Caboodle until September. Have a quick look through the booklet. Again, we are looking at getting you paper copies of the booklets, but we need to leave them for 72 hours before we can let anyone touch them. And if you want a little bit of an extension, especially if you study biology, have a quick look at the extension worksheet, which is on Moodle, on enzymes. Well worth having a look at. Remember that actually rates of reaction, catalysts, etc., are really important in biological systems. So I think that is probably enough from me for the day. Have a lovely day. Please let me know if you have any difficulties with any of this. Thank you very much.